Imagine dropping a glass on the floor. Now, imagine watching those scattered pieces suddenly reverse direction and perfectly reassemble into a whole glass. In our everyday reality, that never happens. We experience time moving in exactly one direction, forward. Physicists call this preferred direction the arrow of time. This one-way street is dictated by the second law of thermodynamics, which states that any isolated system naturally evolves toward greater disorder. It is the reason ice melts, smoke disperses, and glasses shatter. But look closely at the fundamental equations of physics, the math describing gravity, electricity, and even much of quantum mechanics, and a strange paradox emerges. The math works perfectly whether you run the clock forward or backward. The equations allow for rewinding, but the physical rule of entropy locks us out. That constant push toward disorder traps human perception in a strictly one-way timeline. Zooming down to the microscopic level reveals a different set of rules. Before measurement, quantum particles exist as formless probability waves holding many possible states. The mathematical evolution of these superimposed quantum states follows the Schrödinger equation. And just like those macroscopic rules, this mathematical evolution is perfectly time-symmetric. That symmetry breaks during the act of measurement. When we observe a quantum system, we force it to abandon its fluid probability and choose a single state. This diagram illustrates what happens when we try to observe a quantum state. The vertical beam represents our measurement, which physically disturbs the smooth wave, instantly fracturing it into chaotic random spikes. This interaction permanently introduces unpredictable randomness into the environment. Because this randomness is unpredictable, you cannot trace a measurement's result back to its original wave. This creates a logical before and after that cannot be reversed, generating a direction for time where none existed in the math. Researchers from Los Alamos National Laboratory, NIST, and the University of Maryland recently developed a theoretical framework to address this specific measurement disturbance. Their objective was to find a way to monitor a quantum system without allowing that random disturbance to ruin its fragile state. To do this, they designed mathematical signals described as a control Hamiltonian. This framework allows engineers to intercept and manage the noise created by measurement. Here we see the mechanism in action. By continuously monitoring the system's data stream, the researchers instantly apply a precise, inverse feedback signal to the jagged measurement noise, flattening it out. It works exactly like noise-canceling headphones, neutralizing the disturbance before it permanently alters the particle's state. By successfully isolating a quantum system from measurement noise, engineers gain the ability to manually dictate how that system evolves over time. But perfectly canceling out this quantum noise leads to a highly unexpected outcome. Looking at this trajectory model, when the randomness is neutralized, the quantum system is forced to evolve backward. It retraces its exact mathematical path along the timeline, mimicking time flowing in reverse. This is a mathematical reversal of a quantum state. The particle is not physically traveling into the past, as the broader universe continues to move forward exactly as before. Researchers have developed a method to physically hack the trajectory of quantum particles, guiding them against the natural flow of entropy. This concept actually has roots in a 19th century thought experiment by James Clerk Maxwell. He imagined a tiny demon that could sort fast and slow molecules, seemingly cheating the laws of thermodynamics and decreasing entropy. This new quantum feedback framework acts as a modern microscopic version of Maxwell's demon. Because the system extracts information to manage entropy, physicists theorize they can extract useful work from this reversal process, potentially using it to power microscopic quantum batteries. This control addresses the extreme fragility of qubits, a primary obstacle to scaling quantum computers. At this scale, even the slightest disturbance from the environment can destroy a calculation. By learning to control time's arrow during observation, scientists can stabilize these sensitive systems and dynamically fix computational errors as they occur. The ability to error-correct and stabilize these states provides a foundation for more reliable quantum processors. So, what do you think? Will manipulating time's direction at the quantum level actually accelerate the development of practical quantum computing? Drop your theories, predictions, and any questions you have down in the comments section. If you enjoyed this video, give it a like. share it with a friend, and make sure to subscribe for more deep dives into the mechanics of our universe. Breakthroughs often occur when we finally learn how to guide the laws of physics, rather than constantly fighting against them.